Hi there and welcome back to Triplicate. And I know there have been not any videos come out recently. That's because we've been away on the boat and taken the boat down to London, which was an experience. Anyway, now I am back. We're going to move on with the radical synthesizer, the Heresy, and I've had time to have a think about it while we've been away, and while I'm happy with the hardware, that's coming on alright. We got this far. We're using PCBs with long thin tracks on. It's a little hard, it takes a little too much force to push the contact onto the track, and it didn't seem to be linear. You could calibrate that point, and this point would be nearly half a semitone out. So we've got to look into that, which we will do on the next video. But today I think I am going to review where we're at with the sound generation, which is going round in circles basically. So I have made a bit of a decision. Now, our original brief to build this was it was to have no row of ugly black and white switches, i.e. piano key style keyboard, okay. No MIDI, yep, okay. No filters, oscillators, envelopes, etc. And by oscillators I don't mean what we were working on, which was a real oscillator. What I mean is a waveform generator. And finally it was to have attitude. Well, we're hoping to get onto the attitude eventually, but on that kind of note, I really want to get on with making an instrument that plays and makes a decent sound. So I have taken the big decision to actually implement the sound generation as a wave generator and a filter. So this one will have to go for now. Wah, wah, wah. And I am going to take the waveform generator, oscillator as it's called, out of the mean green, and the filter out of the mean green, and implement them. And I am doing that in the background because it makes dull videos saying here, hey, here's some code I've met. But for now, for the rest of this video, I am going to share with you a couple of thoughts and ideas and investigations I've had concerning how real instruments work and how we are going to adapt that to our sound generation eventually. And I'm going to press on with that and probably just do some work off camera, and when I get something that's working nicely, just bring you back and say, hey, look, isn't this good? Okay, so if you look back at videos number 16, 17 and 18 in this series, we did a lot of looking at coupled oscillators and trying to make a sound engine out of those. And if you really want to know, and if you really fancy some heavy mathematics, well, heavy for me, revisit them, but I will recap very briefly. So, our first bowed bottle model was just a simple mass on a spring. And that goes backwards and forwards, and if you give that an impulse, it will vibrate, and we will say that has a frequency, depending on the spring and the mass, of F. So then we looked at this, Same mass, 2 springs, and we found that that has a frequency of square root of 2f. And then we looked at 2 masses, and that can oscillate in 2 frequencies. Both the masses can be going the same way, so that frequency never extends or contracts, so we can consider it's not there. So this will have a frequency of f, and they can oscillate like that, and we found that it will have a frequency of the square root of 3f. Now we can then go on to 3, 4, 5, 6 and 7 and however many, and we found that they all have these funny square root terms and produce very inharmonic spectrums, which is kind of not what we want to make a harmonic instrument. So then we went and tried to set values of the masses so it would give a harmonic spectrum with moderate success. And that was the end of the 3rd video, and then I tried to plug this into the bow bottle model. So you can imagine you have a bow along here, and that's travelling that way, and the mass will stick to the bow by stiction till the force on it gets to a certain amount, and then it'll break free and it'll spin round and it'll come back and stick to the bow by stiction, and so the bow gives it a little kick every cycle. That worked fine. So then I tried to do the same on, say, this system. Let's put it on that one. So here's our bow. Expecting to get a continuous but inharmonic tone, and blow me, I actually got a harmonic one, which wasn't that far away from a sine wave either. At which point I thought I must have done something wrong in the code, and essentially got completely fed up with coupled masses and went and moved on and did something different, like worked on the player interface. However, I then always try and go back and look at a physical system and see how that behaves. So I got a wine glass. So I have here a wine glass, and if you tap it, you get a typical bell-like inharmonic spectrum, but if you run your finger around it, you get a harmonic spectrum. Okay, so here's a recording of our struck glass. Sounds like that. We're going to ignore the bit where it distorts badly here. So let's look at the spectral view. Again, this bit is where it's distorted, and we can see we've got some harmonics, not to mention other small harmonics in between and all sorts of interesting stuff. And if we bring in the spectral analysis, we can see we've got peaks at just over 1,000, 2,000, 300, 400, 4,500, 7,000 and nearly 10,000. Let us look at our finger around the edge continuous tone. We'll play that. Okay, so we can see we've got some harmonics and they look a lot more linear. So if we grab, say, that point, and look at the frequency analysis, we've got just over 1,000, a bit over 2,000, a bit more over 3,000, a bit more still over 4,000, a bit more over 5,000, 6,500. You get the idea. So I have taken, you can measure those on this, you can put the pointer there and it tells you what the frequency is. So I have done that, and I have plotted them out. So the blue squares you can see are no ways linear. That's a curve, and the exact resonances of a wine glass system I would hate to try and calculate because it's quite complicated, but we can see the continuous one looks like a straight line, and if we draw a line on it, so we can see it is a straight line, which is the same as we found with the coupled masses. You let them free run and you get inharmonic resonances, whereas you drive them and you get harmonic resonances. So what's going on here? Okay, so what's going on? Well, let's take a kind of simplified model of our glass. A glass is solid and oscillates basically like any solid, whichever wood, metal, anything, but it's unusual shape, well, not unusual, it's its shape that gives it the inharmonic resonances. So we can kind of model our glass as a bunch of masses on springs. It'll work well enough for this argument, and we're driving it with a bow, which is essentially what our thing around the rim is doing. Now we will give this, as the bow sticks, we will give this one a little push, and then the bow will slip, and this system will resonate, or start to resonate, inharmonically. But at some point it will come round and the bow will grab it again and give it another little push. And for it to be stable, that is kind of resetting it. So we're getting some harmonics, but every time the bow catches and pushes it, we're resetting it. So for the thing to be stable, it's got to do that. It's got to do the same thing every cycle, and if it's doing the same thing every cycle, it's going to have a harmonic output. I guess if it wasn't stable like that, you could maybe make a system where it would oscillate inharmonically a bit and then catch again, and that would push it and it would oscillate inharmonically a bit, and then that catching would be at arbitrary points, so you would get an inharmonic sound, but you don't seem to. Now the glass has a strong resonance at 1,000 Hertz, which came up on when it was both tapped and when it was run continuously, so that seems to predominate. If you tap this, it basically runs mostly at 1,000 Hertz and comes back. I guess it's probably the way it resonates. At the rim, the 1,000 Hertz is very prominent. So that's it, and that's what was happening with our coupled masses when it produced a harmonic tone. It was actually just kicking and picking one resonance, basically resonating at that resonance with a few little harmonics thrown in. So that solves that problem. I'm not sure that's useful. But anyway, it was something over the months I've come to sort of figure out. So I thought I'd share it with you. Okay, so here we have, I used this picture on a couple of the videos of how a typical wind instrument works, a recorder in this case. And yeah, there are some nice pictures of the airflow going either side of the I can't remember the name of it, the sharp edge there. But these are a bit confusing. You know, what is actually really going on here? So I did have a play around and tried to get it straight in my own head and succeeded in doing that. So here is my explanation of what is going on a recorder or recorder-like instrument. Okay, so here I'm using the tin whistle because I can't find the recorder. I suspect it's been hidden from the grandsons who like to blow down it as hard as possible and make a really horrible screeching noise. But it's the same principle. And here we have a little bit of tissue over the end, and if I put it this way, I think this on camera, there you go, so it's quite sensitive to movement. That's just my breath. So let us see if I can line this up and blow down here. And I forgot to mention, I've taped over all the holes, so all the air that's going in here is going all the way down the tube. And you can just see my little piece of tissue moving. So that is, I mean, there's no way of calibrating this, but I suspect that is air moving at, well, goodness, millimeters per second. Okay, so this is what I take to be going on. We have our air blowing in here against this edge, and because of the way fluid dynamics is, it's inherently unstable and will go so far and then collapse and flip the other way. So what we're trying to do is use our tube as a resonance to help it along its way. So say we have our air as just flipped that way into the tube. Now we're talking dynamic here rather than which way the air is actually going, because the air is going very quickly through the tube, but that sudden transition will send a pressure wave, so it's like pressure squeezed in, which will go down the tube at the speed of sound to the end and be reflected. Here's our pressure wave back, by which point our input flow down there will be getting unstable, and that pressure wave will give it a push, so then it will go out there, and that sudden flip from in to out will create a low pressure wave. It will pull the air out, which again will go down to the end, be reflected from the end, come back, by which time our wave going out will be unstable, and you can see in the pictures they've taken there it's very turbulent and unstable, and will be sucked back in again, and we will have another pressure wave going down. And these pressure waves, these pulses of low pressure and high pressure, will be going down at the speed of sound, even though any air travelling down this column will be going like millimeters per second. That's 330 meters per second. So let's take our penny whistle, tin whistle. So the column of air is about 29 centimeters long. So what kind of frequency would we expect that to give us? Okay, so for a wave in a medium, V, the velocity, equals F, the frequency, lambda, the wavelength. and we want the frequency. So F equals V over lambda. Now the lambda is, well, we get a positive pulse and then a negative pulse. So the wavelength is twice that, which is 0.58 of a metre. And the frequency and the velocity of sound is 330 meters per second. So the frequency is 330 divided by 0.58 equals 568 Hertz. Okay, and here is our tin whistle. So if we go into analyze, it's saying 540.8 Hertz. Near enough. So there we go. Okay, well I reckon that's it for this one. Just a little update on where we are with the Heresy, the Radical Synth, and a couple little thoughts on the sound generation part of it, having said I am now in the interim and going to go over to using a conventional synthesizer waveform generator and filter to generate the sound, just to make an instrument that plays. And so next time we will get on to trying to sort out our strings, get to the bottom of the non-linearity and make it so you don't need to press quite so hard to get them to work. And in the meantime, in the background, I am beavering away on this oscillator filter sound generation method, because it's basically the mean green code, and as I say, it's not very exciting making videos of writing code. So until then, I will take my leave and press on. So see you next time, and it's goodbye from Triplicate.
Goodbye.